All right, this is the 7th of 7 videos. We are at the end. I know it's sad. Endings are sad, but this is the end, the last of these 7 videos that comprise one lecture on potentials and fields. In fact, we're not really in fields anymore. Now we're talking about work and energy and things like that. But, you know, it's all in the same sort of vein of trying to figure out what this electric potential is and how to use it and how to get answers by reasoning about it. Okay, so I've got this electric potential. It's doing things for me. What are we going to do? So we've done a lot of different things in this case, and we're going to do one more. It's a ranking task. We've already got the ranking task on eCampus, so you should be able to print that out and follow along, and probably, you know, work it out beforehand, right? That's probably the best idea. So this is the setup. This is what I'm doing. I've got this field here in the white box, and in that field I've figured out what the potentials are. These dashed lines are equipotential lines from 40 volts down to minus 30 volts, and these circles are distances from this point P. P is where a positive charge is starting out. That's where he's sitting right now, and I'm going to let him move around. Okay, and well, I'm not going to let him move around. What I'm going to do is I'm going to move him around. And what I want to figure out is where it takes me the most work to move the thing, right? So I'm going to move things around. So I'm going to move P to over here to A, one distance away on this 10 volt equipotential. How much work does it take me to do that, right? How hard is it for me to do that is the question, right? And so the question is to rank them, right? So I've got 6 of these, A through F, A here, B here, C down here, E over here, D up here, F way over here, and that's out of order, but that's okay. And so I just want you to rank those, all right? So think about how you can rank those and so forth and so on, and pause this, all right? So figure out how to rank them, explain your reasoning, rank them, and evaluate how the quality of your reasoning. How well did you figure out what to do? And then circle one of these things down here. Obviously, you can't circle your screen. Don't do that. Well, maybe you can, but probably that's not the best thing to do. On eCampus, you've got a piece of paper that has these things to circle. Circle those. All right. So let's pause the video. Work on this. You know, try to work this out qualitatively, try to work it out quantitatively. If you can work it out both ways, great. And if you can work it out both ways and they come out different, figure out why, right? And then come on back and I'll explain what I think is going on here, all right? So pause and come back, all right? Now we're ready to go. This will be fun. All right, so let's see what we've got. So what is the work required to do something? Well, basically, if I have to add energy to it, I'm the external factor, then the work required is increasing the energy, right? So this is a positive charge, which means increasing the energy an increase in the energy is going to come with an increase in the potential, right? So if I go from 20 to 30, that's going to be an increase in the potential. None of these little rings actually matter. All right, the rings aren't going to be important for this. What's going to be important is just the increase in the energy, and that's all we care about. That's the whole reason why we like the potential. That's the reason why we like energy methods, is because we don't have to worry about paths or how to do it. We can figure out things just by total quantities that we can calculate. All right, so the first thing I'm going to say is everything below this 20 volt line is the stuff that can increase the work, right? It's harder to move up because this is a positive charge. We increase the potential. That requires me to exert some muscles to do it, right? So it's anything here at the 30 or 40 volt line, that's what's going to have the really strong result, or going to have a positive work. And there's only one thing down there, that's C. So C, it's the only thing that requires positive work. So that's the first one. And I forgot to erase the E, but E is next because it's on this equipotential. Moving anywhere along an equipotential takes no work. Isn't that awesome? So as long as something's along an equipotential, it takes no work. questions like these appear all the time, where they'll say something about going along an equipotential, how much work is done between them, and so forth and so on. You'll see those questions on quizzes and tests and all over the place. So probably a good idea to remember that if the potential doesn't change, if you're moving along an equipotential, no work is done. Okay, so that's E. It takes no work to move along the equipotential. Now we've got a bunch of other ones, and basically we can just keep on going down here. The 10 volt line, everything along it takes the same amount of work to do, and that's F and A. So A equals F, so we can have AF or we can have FA. It doesn't matter because we're ranking and they're equal. Then we go down to 0 volts. That's going to be D, and B is the only thing that's left. It's way down here at minus 30 volts. So actually for A, F, D, and B, the thing's pulling me. I'm not pulling it. So that's the way things are going to work, right? So that's all you have to do to figure this one out. I hope that was pretty reasonable to you. That was reasonable to me. You could have done some calculations as well, but fortunately a lot of times we can do these things without doing any real calculations, and we can just figure things out. And that's the way we like it, right? So I will see you in class on Monday, and everything will be awesome then, just as awesome as it is now, all right? There should be a quiz then, so please think about quizzy things before then. All right, talk to you later. Bye now.